Hi class, so we want to focus on section 4.1 in this video, which is covering exponential functions. So this is out of our Blitzer textbook. So the very first thing I have here is this is from a box from our textbook, but it's just a definition of what an exponential function is, right? So basically what an exponential function is it's a function that looks like one of these two forms, right? Either in functional notation or just an equation using y, right? But we have some restrictions about b. We're told that b is positive, constant, other than 1, right? So constant meaning it's not a variable, it's just some positive number we're putting in, right? That doesn't change depending on what x you put in. And then we're told that x is any real number, right? So x is our input into the function. So in other words, we're going to have some number raised to x, right? Is essentially what the function looks like, right? Like y equals some number raised to x, where b is just some constant number. So you maybe have seen exponential functions before. So just really quick, I just want to graph, graph something like, I don't know, like y equals 2 to the x power, right? So just a rough sketch. It's gonna look something like this, right? Where we'll later find out that the x-axis for a graph like this is gonna be the horizontal asymptote, and then your function in this case is this is an example of exponential growth, right? Where it's increasing really quickly, right? So this is exponential growth, right? And then if you have something similar, like kind of the flip of this, right? So if we kind of flip this over the y-axis, you get a graph that looks something like this, right? And of course, if we think about transformations, right? How do you reflect something over the y-axis, right? You put a negative sign in for the exponent, right? So then this would be the same thing as 1 over 2 to the x, which is actually the same thing as 1 half raised to the x power, right? 1 half raised to the x power, right? Because 1 raised to some number is just going to give you 1 back, right? So in other words, what I'm noticing is that this is the same thing as 1 to the x over 2 to the x, and then you can get to this part using exponent rules, right? If you have a fraction, right? So if you have a fraction like a over b raised to the x power, right? This is the same thing as a to the x over b to the x. So you take the numerator over that power, the numerator raised to that power over the denominator raised to that power, right? So then if you graph these in decimals really quick, you could see the graphs maybe a little more clearly. Whoops, that should be a 2. Y equals 2 to the x, and then y equals, I'll just put in 0.5 to the x. Right? So if we zoom out here, we can see the graph, and you can see the growth and the decay, right? So this y equals 1 half to the x. This would be an example of exponential decay, right? So the idea is, if I have a function that looks like this, I want this function to look like one of these graphs, essentially, right, in order to be exponential. But you'll notice we have some restrictions for b, right? So if you look, let me just move over here. If we look in the notes, right, that definition of an exponential function, we're told in the parentheses, maybe a little more clearly, that b must be greater than 0, right? And also we're told that b cannot equal 1, right? Kind of these two conditions. But really, you can pull pull these apart, right? In other words, this is like saying that b cannot be equal to 0, and also b cannot be less than 0, right? So I put a slash through the less than sign, just like you would an equal sign, to mean that it's not less than, right? So then this case could just pull over, so this would be like b not equal to 1, right? So we kind of have these three cases. Let me grab another color. So we have this case, and this case to consider, right? So with case 1, let's think about and investigate why b can't be 0, right? So let's say, let's just try it. Let's try b equal to 0 and see what happens, right? So remember, my function looks like this: y equals b to the x, right? Or f of x equals b to the x, right? So if I just look at a function, like look at f of x equals 0 raised to the x, what's this going to give me, right? I have 0 raised to x, right? What's this graph going to look like? Well, if you think about this for a moment, one thing that's true is that x cannot be equal to 0, right? So if we're thinking about the domain of this function f, so it's any x such that, so x can't be 0 because 0 to the 0 power is undefined, right? And you can think about this for a moment, because if I have, let's say like 5 raised to the 0 power, that's equal to 1, right? If I have 10 raised to the 0 power, that's equal to 1. If I had 12 to the 0 power, that's equal to 1, right? So in other words, we kind of have this idea that if I have some number raised to 0, we get 1, right? Versus if I have, 0 to, 0 squared, we get 0. If I have 0 to the 5th power, we get 0. 0 to the 10th power, we still get 0. So in other words, if I have 0 raised to some power, this seems to be equal to 0, right? Whoops, and I don't know why I wrote 10. So 0 to the 10th is not 10, it's 0, right? So sorry about that. I don't know if I said 0 also, but maybe I was going a little too quickly there. But anyway, so if we're thinking about the kind of this pattern versus this pattern, if we mix the two, right, 0 to 0, is it going to be 1 or is it going to be 0? We don't know, right? So we call this undefined, right? And in mathematics, right, undefined means that there's no value that it equals, right? Like 2 plus 3 is defined to be equal to 5, right? That's defined, where this is undefined. There's nothing to put there, right? So I know that the domain of this, we have to exclude 0 from the function, right? And then another idea is that x actually can't be less than 0 in this case, right? So let's look at why that's the case. So if I take like 0 to the -5th power, right? This would be similar to having 0 to the -5th power over 1, right? Just having that as a fraction. And what do we do? Like, what if I have, x to the -5th power, right? So this is the same thing as x to the -5th over 1, just like we had written over here. But remember, with the negative exponent, that goes down in the bottom, and you make the exponent positive then, right? You're like flipping it, right? You're moving it to the bottom, right? And then there's a factor of 1 left in the top, right? Because it's like, you can think of this as 1 times x to the 5th. So then this part just moves down here, right? And of course, 1 times x to the 5th is just x to the 5th. So we don't have to worry about this the 1 here, right? Coefficient of 1 here. So in other words, x to the -5th is just 1 over x to the 5th, right? X to the 5th power. Just like you've seen, with exponent rules, probably in a lot of algebra classes, right? In high school, middle school, so forth. So if I have 0 to the -5th power, that would be, kind of like this 1 over 0 to the 5th power. Well, that would be like 1 over 0. But we know we can't divide by 0, right? So this is also undefined, right? So in other words, what we're doing, just to recap what we're doing is we're thinking about this function, and we're thinking about what's the domain of this function, just so we can kind of get a graph, right? So in other words, the domain is that x has to be greater than 0, right? Because we found that x can't be 0, and x can't be less than 0, right? So we'd put a slash through there, right? So if those two things can't be true, then the only items that are left is greater than 0. And so if we have a positive value in there, it's going to be fine, right? It's this idea, right? So if I take 0 to some positive number, I get just 0 back. So as you could imagine, this is just going to be the graph of this is just going to be a horizontal line, right? So y equals 0 to the x power is basically going to be a part of a chunk of the graph y equals 0, right? The only difference between these two, right, is in this case the domain is all real numbers, right? Where in this case the domain is that x has to be greater than 0, right? So if I draw some axes here, right, where this is x and this is y, I'll graph this function in red. What we would have is a hole at the origin, right, because x can't be 0, and then it would just be over top the x-axis going to the right, right? So we'd pick up all these values in the domain, right, and then the output would just be 0 constantly. Right, and you could verify this. We could graph this in Desmos really quick. So I'll just do y to the 0x, and I'll just turn that one off, and you can see that that's my graph, right? It's just this flat line. And remember, your graphing calculator in Desmos, as we saw in the last chapter, does not graph the holes, right? But there should be a hole there, right? Because it's not defined at x equals 0, right? So what we did so far is we verified that b can't be 0, right? So now what we need to do is look at case 2. Why if you have one of these functions, y equals b to the x, why can't it be negative, right? So let's take a look at that. All right. So again, this is case 2. We're still thinking about this function, and we're thinking about why can't b be less than 0, right? So this will go back to exponent rules. So let's just plug in negative b in for b, right? What you would have is y equals negative b to the x power, right? So I just replaced b with negative b, right? So then I could rewrite this expression, negative b, as negative 1 times b, right? Because negative b is the same thing as negative 1 times b. And then we can apply an exponent rule. So if I have two factors like a times b raised to the x power, the exponent rule for this is that each factor inside gets raised to that power, right? So it becomes a to the x and b to the x, right? So this is just a quick review of that exponent rule. So what this would become, right, is minus 1 to the x, and then times b to the x, right? That's what this would become. So this part we already know is exponential, right? But let's think about what this factor does. This factor, when I put in different x values in, is going to essentially alternate its sign, right? So like if I put in, let's say, x equals 1, then this is going to be negative 1. If I put in x equals 2, this is going to be positive 1, right? So this would be evaluating negative 1 to the x, and these are just my x values, right? So if I put in 3, you could imagine, this would be negative 1 to the third, right? Which would be negative 1, right? Where this was, negative 1 to the first, and this was negative 1 squared, right? So then, if I put in 4, we would have negative 1 to the 4th power, which is, positive 1. What if I put in like the 103rd power, right? Negative 1 to the 103rd. So you don't have to, actually multiply it out 103 times. You can notice a pattern that when x is even, I'm going to get positive 1, and when x is odd, I get negative 1, right? So that seems odd, right? That it's just going to keep alternating signs. So like if it's 10, the next one would be negative 10 and so forth, right? So it just keeps changing signs depending on the x value. So let's look at a quick graph of what would this look like. So I can't plug in, two variables into the to the Desmos. It's not going to graph it. What I could do is just plug a value in for b. So earlier we looked at y equals 2 to the x as an example of an exponential function. So why don't I just go ahead and use that idea for here, right? So in other words, let's look at f of x equals negative 2 raised to the x power, right? That's essentially what I want to look at. So I'm just plugging in 2 in for this b, right, into this form that we were looking at. So if I do this, all right, so put negative 2 in parentheses, raised to the x power. Let's see what this graph looks like. Hang on, Desmos isn't wanting to graph this. Hang on a moment. Desmos, or if you try to plug, the function y equals negative 2 in parentheses raised to the x power into your graphing calculator, it's not going to give you a graph. And the reason being is it gives you like a lot of wonky things that aren't typical when a graphing calculator is trying to graph something. So for example here, this is a post that someone posted online. Why doesn't my calculator graph this function? And it looks like this is a calculus teacher responded, and it says if you just choose integer values, right, like negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, right, and it keeps going on forever in both directions, right? So those are integers, right? If we choose integer input values, these are the outputs that we get, right, and so forth. So we can plot those, but you see even these points don't really show like a nice, neat graph, and so forth. But also what's going to happen is you're going to have a lot of holes in the graph, because when you plug in like fractional exponents, you're going to get complex numbers, because a fractional exponent's like a square root. So remember, when you take the square root of like a negative number, you end up going to have I involved, right? So in other words, in between the integers, you're going to have all these gaps, and there's not going to be anything graphed, because it's going to end up being complex, right? Because when you have a rational exponent, right? So that's why it won't graph, and you can see that this isn't exponential then, right? So we can't let b be negative, right? So let me put this back over here, Desmos, right? So just to try to make that clear, if we look at this graph, and let's say we plug in like f of 1/2, right? What you would have is negative 2 raised to the 1/2 power, which is the same thing as the square root of negative 2, right? A 1/2 exponent means 1/2, right? Or excuse me, means the square root, right? Just like if you have 1/3 exponent, means the cubed root, and 1/4 if your exponent's 1/4, that's the 4th root, right? And so forth. So the square root of -2, right, is the same thing as the square root of -1 times the square root of 2, which is radical 2 I, right? So we get this imaginary number involved, so we can't graph that on the real plane, right? Which is what we're trying to graph it on, x, y. So so we're gonna get this wonky graph, right? For integer values, we'll be able to get points, but for points in between, it doesn't quite work out, right? So that's why that's a problem. And then lastly, so the third case, let's see remind ourselves what the third case was. Third case is that b can't be 1. So that's a little easier to investigate. So case 3 is b cannot be equal to 1. So if b is 1, you'd have 1 equals 1 to the x. So this, of course, would just be the same thing as y equals 1. Right? So if I plug in any number in here, you're going to get just a flat line, right? So like if I have x equals 0, you're going to so if you plug in 0, you would have 1 to the 0 power, which is just 1, right? Let's see, would a negative number be a problem? If you plug in, let's say -5, then you'd have 1 to the -5th power, which would be what? That would be 1 over 1 to the fifth power, which is simply just 1 over 1, which is just 1, right? So we get 1 back. If I plug in a fraction, like let's say 1/2, this would be 1 to the 1/2 power, which would be the same thing as square root of 1, which is 1, right? So it looks like, no matter what number I plug in for x, I get just 1 back as an output, right? So we could try to graph that really quick in Desmos and see what that looks like. And let me zoom back in. I was zoomed way out. All right, so now that I'm zoomed back in, you can see that we get what we expected. Y equals 1 to the x is simply the same thing as just y equals 1. We get a flat horizontal line for a collection of all the same points with the y coordinates of 1. So that's not exponential function, right? It doesn't fit one of those categories, right? So hopefully that was helpful. Just thinking about that definition, right? Sometimes in math we just kind of memorize things, but I think it's real important to investigate why, right? So it's okay to ask yourself, like, why is that true? And then you could pull things apart like I just did to kind of think about, why is it the case that b has to be a positive constant and can't be 1, right? So we did that. So then if we want to look at, so here is just some examples of exponential functions. So this first one, we have a base of 2, base of 10, right, base of 3, base of 1/2, right? So notice in all of these you have a constant as your base, and of course we meet our conditions for the base. The base is not 0, and also the base is positive in all these cases. And then we're raised to some exponent. Some variable exponent, right? So that's important. And then below are some examples that aren't exponential functions, right? So if you have a variable raised to a constant exponent like x squared, that's not going to be exponential, right? That's actually just a polynomial, right? Like we've looked at before. And then here, if you have 1 to the x, that can't be exponential either, and we already looked at y, right? Because that just gives us a constant function, right? And then this graph is not exponential, right? Because the base is negative, right? We looked at why negatives don't work, right? We don't get an exponential graph. It looks pretty crazy, right? And then at least we don't get a continuous function, right? And then f of x equals x to the x, right? This is not exponential because you have a variable raised to raised to the same variable, right? That's not going to give us an exponential function. And you could graph it and experiment why, but that doesn't work out, right? And it turns out that when we work through this, it's okay to have something times b to the x out front, right? So in example 1, we look at that, right? So in general, an exponential function, right, might look like this: a to the b to the x power, where only b is raised to x, and then you have some a out front that's multiplied times this, right? So only b is raised to x. So if we look at this example, we're given the exponential function f of x equals 42.2 times 1.56 raised to the x is going to model the average amount spent in dollars, where f of x is dollars, at a shopping mall after x hours. So what's the average amount spent in the nearest dollar after 4 hours, right? So this is a function modeling this phenomena for us that we can use to kind of estimate for some values and understand what's going on with the trend, right? So in this case, A is 42.2 and B is 1.56, right? So if those are what those values are in terms of this form. So for this case, all we simply want to do is find f of 4, right? Because we want to know after 4 hours, right? So f of 4 would be 42.2 times 1.56 raised to the 4th power, right? Just plugging that in for x, and we could get a value for this. Let's see, and I don't think I have a graphing calculator installed on this PC any longer. Let me check. No, that's not it. All right. Well, I'm going to pause this video and download. I think I have the code to download the software for the TI calculator. Let me see if I can download that really quick to use. All right, so I have my graphing calculator downloaded on this computer now, so we can just type this in, right? 42.2 times 1.56, all raised to the 4th power. We can get this amount, and we get this 249 number, right? So we want to maybe round so it asks us to round to the nearest dollar, right? So this number rounded to the nearest dollar, of course, would be 250, right? So if you want to write a sentence, we could say the average amount spent after 4 hours is $250, right? All right, so let's move on to the next one. So checkpoint 1 is asking us to use the exponential function from example 1 and find the average amount spent to the nearest dollar after 3 hours of shopping. And then we want to see, does this rounded function value underestimate or overestimate the amount shown in figure 4.1, right? So figure 4.1 is actual spending after a certain number of hours spent at the mall, right? So if we plug f of 3 in our function, right, we would have, let's see, our function was 42.2, and then the base was 1.56, right, and then this was raised to the x power, but here we're putting in 3, right, so it'd be to the 3. So if I just copy the same thing I did before, I just need to change the exponent to 3, and we can get this result. So this ends up being, approximately, so round in the nearest dollar would be $160. Right? So then if we look at for 3 hours, we can see from the table that the value is $149, right? So we estimated 160, so this is an overestimate, right? So our function overestimates by $11, right? So the function overestimates and this should be just one word, right? So I'll put a hyphen. Overestimates by $11, right? All right, so then next couple examples, we want to graph exponential functions, right? So with these, I'm just going to plug in some x values, right? So we could plug in -2, -1, 0, 1, and 2, right? So we can plug these x values in to come up with the y coordinates. So you could do that really quickly, or I'm just going to go ahead and plug this in my calculator. And I'm going to look at a table. So I'll start my table at -2 and go up by 1, right? So then I can go to my table and we can get these values. So one thing you'll notice is we don't have those written as a fraction, right? This is 0.111, 0.333. But if you plug it in and just do some arithmetic, right? We would have 3 to the -2, right? This is the same thing as 1 over 3 squared. So you can see this is 1/9, right? So if we didn't recognize that 0.11 repeating is 1/9, you could tell that this is going to be 1/9, right? Which is approximately 0.111, right? If you plug in -1 into the function, you get 1 over 3 to the first, right? Which is 1/3. So this is 1/3, which is approximately 0.33 repeating. Right? And of course, if you plug 0 in, we get 1. If you plug 1 in, we get 3. And you plug 2 in, we get 9. Right? And you can plug those into the function or just look at the table in your graphing calculator. Right? So if we plot these values, right? So if I plot -2 and then it's 0.11 repeating, so it's going to be just barely above the x-axis, right? And then -1 is 1/3. So let's see, 1, 2, 3, 4, 5. So each of these tick marks are 0.2, right? So it would be about halfway in between here. Oops. Just want to put a dot here. There. And then we have 0, 1. We can plot that point. Sorry, doesn't like when I hold down too much. And then 1, 3. Right? And then since we know kind of the overall shape, we can connect the dots, right, and get this graph. Whoops. That's kind of bad. See if I can graph this better on here. Oops, that was at 1, 1, 3. Right, so we get something to that effect, right? And we could look at a graph in the graphing calculator, and you can see we get this graph, right? If you wanted, you could get the same window. So our x was -4, to, we'll say 2, going up by 1 each time. And then y min was -1 to 4. We'll leave it keeping going up by 1. So you can see that that's essentially the same graph that we should get, right? Right. See if I can scroll down. There we go. Oops, that's went down too far. All right. So then checkpoint 3 is very similar, right? We're asked to graph this function 1 over 3 to the x. And one thing that it wants us to note is that 1/3 to the x power is the same thing as 3 to the -1 to the x, which is the same thing as 3 to the -x, right? So if you think about how f of x equals 3 to the x, and let's say g of x equals 3 to the -x, right? This is the graph that we drew previously, and that's what's here on the left. And then g of x, we just basically just putting a negative in for the x, right? If you think about transformations, what's that going to do, right? That's just going to reflect the graph over the y-axis, right? Essentially just changing the right, changing the overall shape of the graph, like a mirror image, right, over the y-axis. So if I get some similar xy coordinates, right? So we would have -2, -1, 0, 1, 2, right? What's going to happen is like the y value for 2 is going to become a -2, right? So this would be 9. -1 would be 3, plugging that in. Plugging in 0, you get 1 still. Plugging in 1, you should get 1/3. And plugging 2 in, you should get 1/9, right? And you can plug those values in and verify that. But those are the values that we should get, right? So then if we plot these points, so -2, 9 is going to be, like way up here, right, off the chart. -1, 3 be here. 0, 1. And then plug in 1, we should get 1/3. Right, so 1, 2, 3, 4. So each of these are going up by 0.25 this time. So 1/3 would be somewhere around here. And then 2 and 1/9, would be somewhere around here. And notice that you're going to get a graph, looks something like this, which is a mirror image of what we've gotten before, right? So if I go into my graphing calculator and I'm just going to graph, we can just do this, 3 to the -x, right? Graph that on the same axis, and you can see that how that mirror image is happening right between the graphs, right? Right. All right, so now we want to look at some characteristics of the exponential function of f of x equals b to the x. So the first characteristic you should notice, that we'll notice, is that the domain of an exponential function is going to be all real numbers, and the range is always going to consist of all positive real numbers, right? And then if we look at a graph of the exponential function of the form f of x equals b to the x, it's gonna cross through the point 0, 1 each time, right? Because when you plug 0 in, you get 1 back, right? And then if b is greater than 1, that's where you're going to get this exponential growth happening, right? So an example of that is this blue function, right? This has b greater than 1. And if b is in between 0 and 1, what you're going to find is you get the decay graph, right? So it's going downward as x gets bigger. And then something else to note is that b of x is 1 to 1 and has an inverse function, right? So remember, 1 to 1 function, it passes the horizontal line test, right? And if a function is 1 to 1, we know it's going to have an inverse function. And in the next section, we're going to investigate what the inverse function is, actually. And then the sixth characteristic is talking about the horizontal asymptote, right? So it doesn't touch the x-axis, but so we have a horizontal asymptote at y equals 0 if given this graph, right? So we kind of seen all these things before, but just kind of putting it formally together, right? And then this is nothing new, right, in terms of transformations, but just showing this explicitly. If you add a constant or put negatives in certain spots, right, what does that do in terms of transforming the graph, right? So you can see it's no surprise about the reflections, the horizontal translations, and so forth of how that happens, right, and what's going to happen. So if we want to practice this, checkpoint 4, we have a graph f of x equals 3 to the x, and we want to obtain the graph g of x equals 3 to the x minus 1, right? So you should recognize, what's going on is you're subtracting 1 from the x value. So remember, that's going to shift the graph to the right, right? So let's see. I'm just going to go ahead and get rid of the graphing calculator for now and make some more room. Right. All right. So what we should notice, going from f of x to g of x, is that we have a horizontal shift to the right 1 unit, right? So in other words, if we have a general point xy in f of x, this becomes x plus 1 comma y, right, in g of x. So if we know some of these points, right, it's just going to shift 1 unit to the right, right? So like this point is going to get shifted 1 unit, so it's going to land here as a new point. And we can kind of just pick these, right? So let's see, is there any more that's kind of nice to move? We can move this point. So this point's just going to get shifted 1 to the right, so it's going to be here now, right? This point is going to get shifted 1 to the right, so it's going to be there. Right, this point's going to get shifted 1 to the right. So let's see. I think about there would be 1. Oops. Right? And so forth, right? So all these points just keep getting shifted over 1 unit, right? So we'd have to go 1, 2, so it'd be about here. And then if we begin to draw the function in, whoops. Right, you're going to get a graph that just shifted to the right 1 unit, right? So you could, get some coordinates in here, right? So like if you have x and g of x, I plugged in -2, -1, 0, 1, and 2, like as before. If you plug -2 in, you should get 1/27th. If you plug -1 in, that's 1/9. 0 is 1/3. 1 is 1/3. And if you plug 2 in, you should get 3, right? So if you plot these points, you can also begin to get the shape of a graph, right? So like here's the point 2, 3, right, that we already plotted and so forth. Right, and you can plug that in your graphing calculator too and see a table or see the difference between the two graphs. So then this next one, right, you should be able to notice what's going on between these two graphs, right? F of x equals 2 to the x versus g of x equals 2x plus 1, right? We're adding 1 to the y coordinate, right, in this graph. So it's going to be a vertical shift up 1 unit, right? So from f of x to g of x, we have a vertical shift up 1 unit, right? So a general point xy in f of x is going to become the point x comma y plus 1 in g of x, right? Just like before. So each of these points, like this point, is going to get shifted up one unit. Right, this point is going to get shifted up 1 unit. So it'd be about here. Right? This point will get shifted up 1 unit. This point gets shifted up 1 unit. This point would also get shifted up 1 unit, right? And so forth. So that means this horizontal asymptote will also get shifted up 1 unit, right? So the horizontal asymptote at y equals 0 will now be at y equals 1. Right, so we're going to have horizontal asymptote here. So my graph, if I just connect the dots I have so far, would look something like this. Right? And again, you could graph on Desmos or your graphing calculator and get a much clearer, better picture of a graph, but that's the general idea. Right. So the next thing we want to talk about, and we're going to talk about this quite a bit, is the idea of E, or what we call Euler's number, or it's also called the natural number, right? So Euler's number is 2.718281827, right? You can see at the top, and it's an approximately sign because it's an irrational number, just like pi. So it goes on forever with no pattern, right? But this number is really powerful, and it comes into play a lot in like finance and a lot of different things. So anytime you have like growth or decay, you can use this base E, the natural base. So here's a pretty interesting example dealing with gray wolf population. So if you read through this, give some background to gray wolf population, but what we end up getting is this exponential function, f of x equals and so forth, right? And this is going to model the gray wolf population of the Western Great Lakes, right? So x is the number of years after 1978, right? It says. So what we want to do, right, for part A is using the model, right? According to the model, we want to round to the nearest whole number, what the wolf population of the Western Great Lakes would be in 2014, right? So if we take 2014 minus 1978, right, you're going to come up with the number of years after 1978, which is 36, right? So for part A, essentially what you want to do is find f of 36. So f of 36 would be 1,145 times e to the 0.0325 times 36, right? So just plugging that into this function, and you should get that this is approximately equal to 3,689 wolves. Right, so you can plug that in your calculator and give it a try, but this should be the whole number that you get. And then part B is asking about underestimating or overestimating using the table or the chart here. So in 2014 for the Western Great Lakes, we have 3,686 wolves, right? So it's easy to see that our model overestimated by 3, right? Because if you subtract those, you get 3, right? We have 3 additional wolves, which is a pretty good model, right? 3 over is not bad. And then another important application of the natural number is with compound interest, right? So again, you've probably seen this before, and you're probably familiar with this first formula of compound interest, right? So with compound interest, one thing we have to think about is how many times it's going to be compounded, right? And the more times it's compounded, the better off you are, right? Because compound interest, you're getting interest on interest, right? So I guess in terms of better you are, meaning if it's a savings account, you're going to get more money if it's compound interest, and the more number of times it's compounded, the more money you're going to get because you're going to get more interest on interest. But if compound interest would be like a loan, then that would be bad for you, right? Because then that means you're going to be paying more money. It's better for the bank, right? So whoever is getting the money, compound interest is good for. Right. So so this table is just telling you, if you're compounding semi-annually, right? That means we plug in n equals 2 into the equation, and that means that every 6 months you compound, right? Just twice a year, would be every 6 months. And if you do quarterly, n equals 4, that means you're doing it every 3 months and so forth, right? And of course, you can keep saying like monthly and daily. So like if you're compounding daily, that means you have 365 number of periods you're compounding per year, and so that means that you're compounding every day then, right? So you can see from this equation that t is going to represent the number of years, right? Then a is the amount you're going to have, right, after t years, the balance that you're going to have left in your account. P is your principal, right? That's like your original amount you're putting in, right? And then also there's going to be an annual interest rate that's going to be represented in R. And then you're going to plug in this information in these equations, and you can find these solutions. Right. So with part A, we want to look at so with checkpoint 7, we have $10,000. We want to invest that at an annual rate of 8%, and we want to find the balance in the account after 5 years. If A, we do quarterly compounding, and then B, if we do continuous compounding, right? So what we know is that the principal equals 10,000, right? We're also given R, which is 8%, which we can represent that as a decimal as 0.08. And then we're also told that t equals 5, right? 5 years. So if t was given to you as 10 months, you would have to turn that into years in order to plug in the equation, right? So p should always be in dollars, r should always be a percent in decimal form, and t should always be the amount of time in years, right? Those are the formats of each of the variables that we should be using to plug in. And then for part A, we're compounding quarterly, so I know that n equals 4, right? And you can tell from the table or just knowing that there's 4 quarters in a year, right? So then for part A, I'd be plugging in the first equation, so I would have A equals, and then plugging in P, so 10,000, and then times 1 plus 0.08, all divided by 4, and this would be all raised to the n times t power, which would be 4 times 5, right? So you can plug this into your calculator, and you should get approximately $14,859.47. right? So then part B, we're doing continuous compounding is the difference. So I want to use the second equation for continuous compounding. You have A equals P times E raised to the RT power, right? So in our case, the principal is 10,000, and then you'd have E, and then your rate is 0.08, and then the time is 5, right? So if you plug this in your calculator, you should get approximately $14,918.25. Right? So real quick, I just want to verify those solutions in my calculator in case you have trouble inputting those. Right, so for part A, right, you would put in 10,000 and then times 1 plus 0.08 divided by 4. Whoops, not times, divided by 4. And then this is all raised to the 4 times 5 power. And then you have to hit enter, right? And you can get that value. And if you don't have an up-to-date version of the graphing calculator, like if you hit the like if you have an older version or an older older calculator software, when you hit that exponent button, it might do like this caret symbol, and then in that case you're going to have to do 4 times 5 in parentheses, right? So that way it follows order of operations. But this software I have is up to date, so notice that 4 times 5 is already all in the exponent, so I don't have to worry about that. Right? And then if you want to input part B in your calculator, right, we would just hit 10,000 and then times, and then we want this button, e to the x. So you'd hit second, and then the natural log button gives you e to the x, and then I would have 0.08 times 5, right, in the exponent. And similarly, your calculator might prompt you with that caret symbol if you have an older calculator, so you'd have to put the exponent in parentheses. Right, if I hit enter, we get the same value that I had gotten, right, rounded to the nearest cent. So these two numbers are rounded to the nearest cent. Right. So that's all of the notes, but I have just a couple other things, just kind of an extension to this section. So the first thing I want to do is let me open up the textbook. I want to point out a few things in the text in this section. So I want to look at page 470 and 473, right? All right, so just bear with me as this loads. All right, so looking at page 470, what I wanted to look at is this technology piece. So what it's saying is as n gets greater towards as n approaches infinity, the graph of y equals 1 plus 1 over n to the n is going to approach the graph of y equals e, right? So in other words, another way to kind of state this, let me just get some blank paper here. Right? So in other words, what it's trying to show us is that as as n approaches infinity, right, then f of x, or no, they used n. Let me do f of n. Right? Then f of n, if f of n equals 1 plus 1 over n to the n, this is going to approach e, right? So in other words, if we were to write that with limit notation, the limit as n approaches infinity of 1 plus 1 over n raised to the n is going to equal e, right? So if we use the limit notation, right? So something interesting about this is 1 plus 1 over n to the n. We can relate that to the compound interest formula that we had earlier. So this would be n to the t, right? So what, how are these connected? Well, let's let t equal 1 year and p be equal to 1, right? The principal equals 1, right? So I can put a 1 here, a 1 here, and then they're equivalent, right? Well, no, this is r, right? Excuse me, that was r. So then if we let r equal 100%, that would equal 1, right? So then now these would be equivalent, right? So in other words, if I invest $1 in a compound interest account with 100% interest rate for 1 year, then if as n gets larger and larger, so the more times I compound, this whole amount is going to approach the natural number e, right? So roughly $2.72, right? If we round that to the nearest cent, e was what $1 will turn into, right? And I have a couple of cool videos I'm going to share with you that dive into this concept a little deeper, and I think they're really, really well done videos, right? So I want to share those with you. And then the other thing I wanted to check out really quick was page 473. So this is just understanding continuous compounding a little more. So the idea is that with continuous compounding, we're continuous all the time. So in other words, n is going towards infinity, right? The amount of times we compound, it just keeps getting larger and larger and larger. That's the idea behind continuous. So you can see here, as this is written out, let me zoom in a little more. Right. So you can see how this is explained, that if we start with our equation a equals p times 1 plus r over n raised to the nt power, then all that was done between these two steps is they had rewritten this in this form, right? And notice these exponents. If I take n over r times r over t, I get nt back, right? The r's will cancel out. So we know the exponent part is equivalent. And then, so since we replaced our n with n over r in a sense, right? Then we need to put n over r here as well, right? So then, if we keep going, we can let h be this n over r. Then you're going to get this equation, right? And then remember, as h grows towards infinity, so before we looked at as n grows towards infinity, but this time as h grows in infinity, this inside part is going to become e, right? This part in brackets. So then I can just replace this part in brackets with e, and then we get our equation p equals rt, right? So we can derive the continuous compounding formula from the previous formula with the idea that n goes towards infinity, right? The amount of times we compound, right? So it's just growing really, really large, right? In terms of the number of times we compound, right? All right, so that's all I wanted to go over it with the notes and out of the text. And then, just one other item. So the two videos I'm showing, one is this video from Numberphile, And just to clarify, this gentleman is from the UK, and in the video, he's going to use some terms that you may not be familiar with. So you're familiar with the concept, but so in the UK, they use the term gradient instead of slope, but it means the same thing, right? So they just use the term gradient instead of the word slope. But it's the same definition, same concept, right? And then also they might, they use, instead of saying math, they say mass, right, with an S at the end. But that's a good video. And then I have another video. It's a math teacher from Australia, Eddie Wu. He has a good video that walks you through the same concept that I just briefly went over. I could do it the same way that he did, but I didn't want to duplicate the videos. So after watching these two videos, you should have a better understanding of what E is, and so forth. All right.